The next important aspect in the neural net part is the activation function. You remember we spoke about the activation function even in the perceptron. There are we only spoke about one simple activation function there, right? It is a Hart threshold part. So, now we are going to be talking about sigmoid, hyperbolic tangent, rectified linear unit and also a leaky rectified linear unit, and finally softmax. So, all are useful. You would see in many cases sigmoid and softmax. Softmax is usually used at the end of the network layer or at the output layer. Sigmoid, tanh or other hyperbolic tangent, ReLU are all used in the hidden layer portions. Okay. Why do we need different sets of activation functions? So, we will talk about that now. Okay. I do not need to explain this in detail. A Hart threshold is something where if a value is beyond a point, it is 1, otherwise it is equal to 0, right. So, this is a Hart threshold that we used in the perceptron. So, we will now get into the very interesting activation function called sigmoid. Sigmoid is a nonlinear function. Okay. So, it converts a set of values that you provide and squashes it into the sigmoidal function as I had shown here in the graph. Okay. So, it actually squashes the values in the range of 0 to 1. So, you have 0 here and then here. So, any value that you provide to this activation function, it will always be limited to this range 0 to 1. And then we have a tail. There are, this region is called a tail region. Okay. So, in this particular region, if your value that you are computing in the H1 in the hidden layer, if you are getting it here, they will be saturated to either 0 or if the values are here, it is equal to 1. So, every time when you see that you are very quickly getting into this space, you will notice that you are getting into the trouble of learning. Okay. Here in this case, there will be no learning since the values here every time when you start computing, the value would always be equal to 0, right, like we had seen in the bias part in the XR computation, right. So, I told you that we are going to be removing that bias because the weight is 0. When the weight values are 0, there is going to be no learning that you will get, or if you have it at this point as well, there will be no learning. So, we ideally want to keep all the values in this region. Maybe let me use a different color here in this region. The sigmoid outputs are not 0 centered. So, as we had seen here, 0 is here and then 1 is at this point. It is desirable, or rather it is undesirable to have all the values squashed near the tails where the gradient is 0. So, the reason why the gradient should not be equal to 0 is if you remember our calculation of weight is like this. This is the iteration number . Okay. So, this is our gradient part, right. So, every time when we want to adjust the weights, there has to be some value associated with this. If this is equal to 0, that means there is going to be no more learning, or if the system has already learnt it. And if you very quickly reach this stage of delta W equal to 0, that means there is something wrong with your input, or something wrong with your network design, something wrong with your weight initialization and so on. Okay, so you may want to check your architecture and the input parameter that you are giving, so that the network does not get into the stage of delta W equal to 0 in the second iteration or third iteration itself. Okay. So, we need to have some difference between the previous iteration and this iteration, so that this value is not equal to 0. That means, we want to have some gradient managed or maintained. When you have a gradient which is in this space, then we are doing good. And if your gradient, if you are already into this space, the gradient would be equal to 0, there will be no learning in the network, right. The learning or the model preparation is all about finding the right values of the weights, isn't it. So, in order for us to get a very stable weight matrix, so you need to have a good activation function that is differentiable. Okay, note the word differentiable. If the activation function is not differentiable, then it is not possible for you to do the learning for the neural network. That is why sigmoid is chosen. Okay. So, there are different varieties you will get, and ultimately we do not want to have a very long tail like these, because the values would very quickly saturate to 0 or 1. Okay, this is one activation function. Then second one is a hyperbolic tangent. So, this is again very similar to the sigmoid, but only difference that you notice here is the range is between -1 to +1. So, you will see this in many recurrent neural network models. So, in the hidden layer computation, you will notice TANH will play a great role in terms of translating or the squashing the values between -1 and +1. So, again you have a function which is differentiable. Okay. And you have one more activation function called rectified linear unit. So, again it is similar to sigmoid or the hyperbolic tangent, only change would be you have only a tail here and you do not have anything. You can see that it is continuously differentiable in this fashion. So, you always have some value associated. Okay. Again it makes sure that there is no 0. So, that most of the values would always be kept in this region. So, that when you do the error correction mechanism, you have some delta value available for you, so that the system learns. Okay. So, it produces an efficient propagation of the gradient, and also it is computationally efficient. So, you do not need to compute that, if you use the sigmoidal function, right, and this is pretty simple. You just very similar to your max value 0 of x. So, it just tries to find out whichever is the maximum, keeps that value. Okay. So, here it is always. So, it is very easy to implement as well. Okay. And then it is scale invariant, does not matter how many ever times you multiply the value with scale factor, it does not change. The only difference between those sigmoidal and hyperbolic tangent is this is not a bounded function. So, the values can be anything, depends on what value of x you get, okay. And it is also not 0 centered like sigmoidal. Okay. So, I have given a simple implementation of all of this, and like any other application that I am showing as a demo, this also is available as part of the GitHub. So, you can take a look at this. This is a very simple implementation. Normal, if you include this as part of the class, a network class, you probably won't have this. You just input sigmoid x. Okay, if it is part of the class, maybe a Python class, you will have this as x. And then still, since you are going to be using derivatives of the sigmoid, okay, in the next stage of network building, we will also have another variable instead of this. Sorry about that. Sigmoid false. So that when you pass the value, either you want to find the sigmoid or you want to find the derivative of this. Okay, so in one simple function, you can achieve both. Okay, so use NumPy. It is, there is a big debate going on in the Reddit in terms of either it is NumPy or NumPy or something else, right. So, I will be using NumPy or NumPy, whichever comes to at that point in time. Okay. We have tanh. It is very simple. Tanh is okay, and this is what is implemented. And then ReLU, I use a maximum. I am just using a very simple thing, which is between 0 and the value. I am not using the leaky ReLU that I had shown earlier. And then the next one is softmax. We will talk about that and then come to this one. So, in this case, you want to find the sigmoid of this using this function. You need to provide the input, the weight vector and the bias, and it will automatically give you the sigmoidal value for that. Okay. All right. So, we are going to be having more number of classes that you want to figure out. As I mentioned earlier in the previous lectures, if you have collected a lot of documents related to the computer science topic, you would like to have a folder called operating system. You want to have a compiler designed for one folder, and then you want to have discrete mathematics and so on and so forth, right. So, there are going to be multiple classes that you will find in the real situation. So, we should be able to accommodate the multiple classes in the case of a neural net as well. So, how do I accommodate that? So, most of the activation that function that we are talking about either squashes the value between 0 and 1 or -1 and +1. So, it is going to be very difficult for me to use multi-class using that, right. So, if you are having several values, I can't say that use the value for class 1, this for class 2, 3 and so on, right. So, instead we need to have a separate decision function that allows you to create multiple classes in itself. So, let us talk about that. We need this for document classification. Even in the sentiment analysis, especially in the movie reviews, you want to find out whether the sentiments are positive sentiment, negative sentiments, neutral, or it is not related to movie. For example, you have received a lot of documents, out of which one document is an outlier, meaning that the document does not belong to any one of the movie reviews, it is something else. Okay. Again, you want to find out whether the word that you are talking about is positive, negative or something else. Okay. Let us put it as R. So, in those cases it is necessary to have a decision function that allows us to predict more number of classes and not just 2, right. as I mentioned, the extension of the case function is very hard to manage. So, we need to definitely have one function that allows us to predict more classes. That is where softmax comes into picture. Okay. So, it has to take a set of vectors of size n and then finally creates a k class. Say for example, I have a network that takes input parameters such as these, and this is my input layer, and I have a hidden layer and they are interconnected, and then I have output layer, again they are interconnected in this fashion, and it should output k classes. Okay, let us assume that I have more of these. So, k classes. So, the values should be able to tell me whether the one that I have recently computed using the network belongs to one of the k classes or not. So, that is the idea of having a k classifier in the neural net model. Okay. So, let me give you one example. Let us assume that we have captured all the words, okay, as a dictionary, and then we have created the one hot vectors for all the words. Okay. So, you know what one hot vector, right, for each word. Supposing if we have about 100 words that we are going to be using for the training, we will have a vector containing 100 elements, and the index of that element would point to the word that we are talking about, right. So, I am going to be inputting this 100 elements, one hot vector into this, and then at the end in the output layer I want to be able to predict whether it is one of those 100 words. It is not about positive or negative, especially in the case of word embedding. This is what we are going to be doing. Okay, so, I am going to be inputting one word using the one hot vector, and then the weights are initialized in some fashion, and I have more than one hidden layer, rather hidden units. Let us assume that is about 100. Okay. And then I have k classes. Assume that there are 100 classes that we are going to be looking at, meaning each word will be considered as one class. Okay. So, when the output is generated, it is not going to be in an ideal situation like one hot vector, right, in this way. So, it will have some values. All the elements or all the neurons will have some values. Let us say that they are ranging from 0, 1, 0, and so on. And they are not bounded by some way. So, what we want to do is we want to see whether the output value, since we are expecting an output very similar to this, values except for this particular index, let us assume that this is the 35th element. 35th element should have some value, rest of them should have 0 values. But ideally, since we are doing the computation in the real space, it is not going to have 0 or 1 in the binary form, there is going to have some value. What I want to these? Okay. So, I want to have a distribution of values between 0 and 1, and then the 35th element I want that to have a higher value, when the network is trained very well. So, when the network is not trained, any value in the output element could have a higher value, correct. So, for me to distinguish which one should have the right value, I need to have a proper distribution of values in this case. So, what we do is we do a softmax computation where the values of the output would be translated into a probability distribution, and every element will have a probability value, and the sum of all the values, if we take it, after we translate this into softmax, if you push it through softmax, we will have again a different set of real values, and if you sum all these values, it will be equal to 1, that we know, right, in the probability distribution part. So, we are distributing the probability mass of 1 to all the elements, 100 elements in this vector space, and then only one of that would be should be having a higher value, rest should be having a very low value, so that we can propagate the error back. So, in order for us to do this, we use the softmax, and softmax picks up the values between 0 and 1. Every element will have some probability, and we have the entire thing as a probability distribution. And when the 35th element is not equal to 1, but let us assume that 23rd element is closer to 1, that has the higher value, we know that there is a error. That is not the word that I am expecting. I am expecting a word where the 35th element should have a higher value. So, now we know that there is an error, and then do the back propagation. So, for you to do that operation, we require softmax. I will talk about this in detail later though, but I thought this is essential for you to understand why we are bringing in the softmax. Okay. So, this actually normalizes the net output, and then the classes are really well separated. So, when you do that, after a good amount of training, you will see that the 35th element is gaining more and more value in the probability distribution. Okay. A simple implementation would be as follows. So, you have the input and the output and the bias, and we need to find the softmax for W. When you input W x and B, it should give you the distribution, and if you do that, you will see in this case we are feeding the W as arrays, and then we have some x values, and then the y values are computed using W x, the dot product of W x and W and x, and then it is summed with the bias. Assuming that the B is also having some weight values that I am not showing here. When you run the softmax function, what you get is this. Okay, so, it is a distribution, or the values are distributed, and you can see that the middle value has a higher probability.